Welcome to Learning with PPS. In this video, we are going to discuss about dining philosopher problem. Dining philosopher problem is one of the classical process synchronization problem. Yes. So in the dining philosopher problems, assume that five philosophers from P0 to P4 who are sitting around a circular table. A bowl of the rice is placed at the center of the table. Five chopsticks are placed in between two philosophers. Okay, here a philosopher can either eat or think at a time. If the philosopher is not eating, he can think. These are all the activities for each and every philosopher. Here the constraints is each philosopher must pick two chopsticks in order to eat. And one more thing is no two adjacent philosopher can eat at the same time, because if the suppose a philosopher want to eat now, that time he has to pick two chopsticks, either left or right. Okay, so this is the constraint and activity of the dining philosophers problems, right? So here we have four problems. One is it is not possible for eating of two adjacent philosophers at the same time. Okay. Second one, assume that at a time all the philosophers become hungry. So each philosopher can take one chopsticks at the time. So that time each philosopher has to wait for getting another chopsticks. That time none of the philosopher will going to eat, because each and every philosopher has to wait for getting another chopsticks. That time deadlock will be occur. So the major problems of dining philosopher problems are, one is deadlock, another one is starvation. So deadlock occurs when all the philosophers are blocked and waiting for a fork. So in the image you can see that all the philosophers pick one chopsticks and waiting for another chopsticks to eat. So that time all the philosophers are blocked and waiting for a fork. So creating a circular dependency where no one can proceed. Starvation, in the sense, it is a longer waiting process. Starvation happens when a philosopher repeatedly try to take a fork, but it consistently interrupted by others. Now that time the starvation will occur. Okay, that is starvation in the sense, when we are talking about the priority scheduling, that time whenever a higher priority process will come, the OS will execute the higher priority process when we compare with the lower priority process. That time lower priority process has to wait for a long time to get into the CPU. The same scenario is followed here also. So deadlock, it is a situation in OS where two or more processes are unable to proceed because they are waiting for other process to release the resources, which means, for consider the scenario P1 P2 P1 P2 R1 R2. P1 P2 are process, R1 R2 are the resources. P1 are assigned to R1, P2 are assigned to R2, but P1 need R2 and P2 need R1. This time that situation deadlock will be occurred. So that time none of the process is going to be executed, all the process are gets blocked. Okay, so starvation, it occurs when the process wait for an infinite time to get the resources it needs. So these are all the problems for deadlock. Now we are going to provide the solutions in. So this is a image for deadlock. So the same scenario, process P1 is assigned, resource R1 is assigned to process 1, but it waiting for R2. R2 is assigned to P2, but P2 is waiting for R1. This time deadlock will be occurred. This is called a circular wait. Okay. Yes, now the solution. So for solution, in the sense, here we are going to provide the solution with the help of semaphores. Okay, now we are using the binary semaphore of 5 chopsticks, each represent each chopsticks. Okay, so first one, philosopher want to eat now, that time he has to invoke wait system call. Okay, wait function. Philosopher 1 na corresponding chopsticks will be decremented to 1, sorry, decremented to 0. So initially all the chopsticks values are 1. Whenever you are whenever the philosopher want to eat now, that time the corresponding chopsticks will be reduced to 0. For example, suppose P1 want to eat now, that time C1 and C2, okay, will be reduced to 0. So that here we are invoking weight of chopsticks of I, weight of chopsticks I plus 1 modulus 5. Okay, so this is the entry section. Eating is under the critical section. So we have to ensure that after eating, each and every philosopher has to put on the chopsticks. Then only we can assign some other philosopher to eat. So after putting the philosopher has to start thinking. Okay, because activities of the philosopher only two, either he can eat or he can think. Okay, so signal of chopsticks I, signal of chopsticks of I plus 1 modulus 5 indicates that that is the put down of the chopsticks. So that time the semaphore value will be incremented to 1. So that is a green signal for other process, other processor in the other process, in the sense other philosopher. So other philosopher can make can make a call to wait function to occur the chopsticks. So after eating is over, the philosopher has to put on the chopsticks. If the philosophers fail to put on the chopsticks now, that time also deadlock and starvation will be occurred. Okay. Yes, these are all the alternative solutions for the dining philosopher problems. Almost we can use 4 philosopher with the 5 chopsticks now, that time we will avoid deadlock. When the philosopher has to ensure that when both chopsticks are free, the corresponding philosopher can eat. Then we can provide another approach, that is odd philosopher, that is P1, P3. Okay, odd philosopher can use left and right chopsticks. Even philosopher can use right and left chopsticks. These are all the alternative solutions alternative solutions for preventing the system from deadlock. So thank you for watching. Those who are not subscribed channel, please subscribe the channel, share the concepts. Okay, so thank you.